Recording. Hello, everybody, and welcome to this session. And today is visiting our game of primes after a very, very long time. And the last time we spoke was in May of 2020. The world was very different back then, and I was in a different place. And it's good to restart on it. So the group theory thing, we will currently keep it on hold for a couple of classes, and by that time a lot of updates will happen, and I will share with you the more recent discoveries 3 weeks later, perhaps, once I formulate some results. And until then, we will talk about game of primes. Okay, so first of all, to those of you who might have forgotten about it, it's a cellular automata. We have a grid full of numbers, and we define a few rules, and we say whether a number will be excited or whether a number will be dormant. And then on the interface, if the number is excited, it is colored red, and if it is dormant, it is colored white. And let us look at that interface again, so that we can refresh our memories. Okay, so we have this, right? And I wish to remind you all that we can decide the size of this interface. We can make it as big as we want. We could have it as small as we want. For example, it could just be one number, right? Or it could be 10 by 10, which is 100 numbers. There are three things here which we can decide, which is completely in our control. Let me repeat those three things. The first is the size. Okay, so it could be a 10 by 10, it could be a 50 by 50, it could even be a rectangle, so it could be 10 by 5. The second thing is the starting number, and right now the starting number is 1, and we can decide it, and we can decide what the starting number should be. The third thing is the gap between the numbers. Okay, so we have consecutive numbers here, and we have to decide how far apart should they be. For example, right now I have a gap of 1, which means I'm having consecutive numbers, all the natural numbers from 1 to 100. If I make the gap 2, then it is 1, 3, 5, 7. Now I only have odd numbers. Or if I make the gap 4, now I have numbers which are all 1 mod 4. So these are the three things in our control, and based on these three things, this game plays out differently, and we observe different patterns, and based on that we come up with a few claims and conjectures, and then we try to prove them, and we try to understand why they work, with the goal of studying prime numbers and studying prime gaps. And if you might recollect, there's also a music side to this, and we will not do that too much in our session now, because it's more of an entertainment factor. But you can listen to music, and you can turn it on, and it will play based on the numbers that are excited. So based on how many numbers that are excited, we can have different tunes being played, so we can keep track of the sound, and we know when a cycle has happened, and we know what is going on with the grid. These are the few things that we had spoken about in our previous discussion about this in May. Okay, now let us see what happens. So let's start with this basic grid, and let's go with the 4 by 4 grid, and let's watch what happens. So I do next. Okay, so the music is on. Let me turn it off. So how does a number get excited? If a number is surrounded by 3 or more primes, it gets excited. And once a number is excited, we treat it with the same importance as a prime number. So prime or composite is eventually going to be treated with the same manner as excited or non-excited, because if a number is excited, we treat it like a prime number for future states, right? So in the first state, when nobody is excited, we are only looking at primes. But once you have few numbers excited, then you check for excited, and you also check for primes. So you look at a particular cell, and you look at its neighbors, and you count how many numbers that are there which are either excited or primes. And if the total is 3 or more than 3, then the cell in question also gets excited. That is how a person can get life. How a person can die in this game is if you are surrounded by too many. That is, if your neighbors you have more than 3 neighbors who are either excited or primes, then you go back to becoming dormant. And also there was another rule, if you might remember, that you can die due to loneliness, which most of us are now experiencing in this quarantine situation, but that can happen here. So if there is a cell which is excited, so he somehow became excited because he had good neighbors, but now due to some situation, nobody around him is excited, and there's no prime, there's no excited state, nothing around him. So in that situation, he goes back to becoming dormant. Okay, so those are the few rules, and let us refresh them and let's see what happens. Now in the first state, we have these 5 numbers that got excited, and let us look at a few examples and see why they got excited. Let's look at 11 and let's also look at 3. So in the beginning, 3 was surrounded by 3 prime numbers, which are 2, 7 and 5, right? It has 3 numbers around it which are primes. So because of that, 3 got excited. What happened to 11? 11 is surrounded by 5, by 7 and by 13. So that is how 11 got excited, and in the same way the other primes, other numbers also got excited. Now the moment these people got excited, we quickly realized that 6 will now become dormant because 6 has too many neighbors around it, right? So just think about 6. 6 has 1, 2, 3, 4, 5, 6 numbers around it which are either prime or excited, and that would mean that in the next state 6 goes back to becoming dormant. Can we check what happens to 12? Interesting situation, because 12 is only surrounded by 3 primes, but you have to realize that if a number is excited, it is treated with the same respect and value as a prime number, which makes it the fact that 12 is now surrounded by 4 dangerous numbers, which will make 12 also dormant. Okay, so 6 will be dormant, 12 will be dormant. What happens to 3? 3 is surrounded by 2, by 7, by 6, by 5, becomes dormant. What happens to 7? 7 is surrounded by 3 excited states on its right side, and it has 2, which is a prime above it. So again, 7 also becomes. So all these numbers become dormant, which is really interesting. So all of them had a shelf life of only 1 day. But because these people got excited, that ripple effect was so large that we will see now what happens to the rest of the grid. Watch closely. 3, 6, 7, 11, 12 go back to turning white, but around them, a lot of people will turn red. So these 5 numbers which were initially red have now become white, but because of that we have 5 new numbers that have become red, and that now changes the game. Now what happens is, because these people are again excited, 6, 3, 7 and all these people can get excited again, because now they have neighbors around them, right? Look at 6. 6 has 4 excited neighbors around it, and it has 3 primes, which is too much in fact. So 6 gets excited again. 3 will also get excited because it has a prime number here and it has 3 excited neighbors. 7 also gets excited, does it? Yes, it has 11, it has 3, it has 2, it has 10. So all these people get excited again. There you go. The previous people remained excited because they did not have too much of overcrowding, and we can look at that reason, because look at 10 in the previous situation. 10 was surrounded by these 3 numbers, 9, 16 and 15, which are all composite numbers. So it didn't really change 10. 10 was remaining alive even to the next day. And it becomes like this, and now we reach this situation where every single number in the grid is excited except for 16. Right? Every single number is excited except for 16. Now this is a crazy situation, because I can tell you one thing for sure, and I don't have to know too much about this game. This grid will drastically change in the next round, and that is the trivial observation that anybody can make. And the other trivial observation that anybody can make is 16 will get life, because now 16 is surrounded by 3 people and all 3 are excited, so 16 will get life. My question to you is this: without me going to the next state, without you calculating too much, can you predict how many of these other people will die in the next round?
All.
You're saying all. Okay, just type in the chat box. Other people can type in the chat box. Watch very closely. Is it all, or is it some, or is it many, or is it very few? Just type whatever your opinion is. What will happen now in the next state? Out of these 15 people, how many of them will die? Just make a guess. Somebody is saying 15. All 15 will die. Okay. Is someone else having? Is Sundar is saying everything except, okay. Vishak is saying 12. Okay. Very nice. Very nice. So Sundar is saying everything will be dormant except the corners, and I think that's right. Because you should remember one thing about this game. Everybody has neighbors, but everybody does not have the same number of neighbors. And you should pay attention to the rules very closely. To get life, you need 3 people around you who are excited or primes. But to lose your excited state, you need more than 3. So if you just have 3 around you which are excited, you will continue to live. Nothing will happen. Only if you have 4 or more, then you can have a problem. So we know for a fact that 1, 4, and 13 will not become dormant because they only have 3 neighbors. So no matter what the situation is, these 3 will maintain their state to the next round. So everybody else will die because they have too many neighbors, and we know that the entire grid except for 16 is there. So this is what happens. So we correctly predicted that 16 will get life, and we also correctly predicted that 1, 4, and 13 will remain alive. And since, as most of you anyway predicted, everybody else is becoming dormant. Does anybody have any guess about what should happen next? No, because we cannot predict it. Maybe this is a small grid, so we can come up with a rough guess. But in case of a large grid, we cannot, because we have no idea what is happening in the middle. We don't know how many primes are there. But we know one thing for sure. We know one thing for sure. We know what will happen to these 4 corners. And to study what will happen to these 4 corners, we do not need to know anything else about the grid. We just have to observe the 3 neighbors. The lucky thing for 1, for 4, and for 13 is the fact that they have at least one neighbor who is a prime number. 1 has 2, 2 is prime. 4 has 3 and 5, which are both prime. And 13 has 11. They're not excited, but they're all primes. So each of these 3 corners, which is 1, which is 4, and 13, has at least one prime neighbor. So the loneliness rule, which was the third rule that I told you about, will not apply to these guys at any point of time in this game, because they can never be lonely. Correct? They can never be lonely because there is at least one neighbor who is a prime. And in some situations, you might also have excited neighbors, but we don't care about that. We know for a fact that there is at least one neighbor who is prime. So we conclude, we make a very strong claim early on in this game. We have just gone 4 or 5 states into this game, and we make this claim. 1, 4, and 13 will never die. They will never die. No matter what happens to the rest of the grid, they will never die because they're already excited. And remember, to lose your excited state, there are 2 things that can happen. Either you are surrounded by too many people, overcrowding, or you die due to loneliness. So think of it as a real world. If a person has to die, let's forget about diseases and accidents. Just let us think about the natural order of human evolution. If a person has to die, there are 2 reasons. Either he's surrounded by too many people around him, which means that there will be fight for food and water and etc. So somebody will die, or he's not surrounded by anybody. So he'll die due to loneliness, and he doesn't have a family, and he will not be able to find food, nothing. So in the case of 1, 4, and 13, we know for a fact that they will never be lonely because they have a neighbor who is a prime. But we also know that they can never die because of overcrowding, because they only have 3 neighbors. They have picked some beautiful houses in this city such that the houses are located at the very edge of the town, right? They're all in the corners, and they will only have 3 people around them, even in the worst case. And we know from our rules that if there are 3 neighbors, that is not enough to kill you, that nothing can go wrong. So once 1, 4, and 13 got life, they will be alive forever. When I say forever, I mean till the end of the universe. But 16 is not so lucky. Although 16 has picked a good house, and he will only have 3 neighbors around him, so he will not die due to overcrowding. He will never be surrounded by too many. His neighbors are not interesting people, meaning for our purposes, they're not interesting. 9, 10, and 15 are composite numbers. So what will happen is, because 9, 10, and 15 are composite, if they are not excited, then 16 is lonely. Right? 16 now doesn't have any neighbor who is a prime, and it doesn't have any neighbor who is excited. So the only way by which he can stay alive is if one of them is excited, because they can never be prime. 16 is unlucky. 1, 4, and 13 will live forever, and the rest of the board, things might happen randomly. So you see 1, 4 and 13 are alive and 16 is dead, and we have other people coming. So now let me just fast forward. Now we reach the situation again. This brings us to the most important point of our game, meaning this is where almost all the research will ever be on this game, nothing else. So the dying, the living, those are all easy rules to understand, and that is just how to start this ecosystem basically. But the interesting patterns happen now. What has happened? We reach this pattern and a composition of alive and dead people, combination actually, not a composition, a combination, which we had seen 3 days back. 3 days back meaning in the game I define each day to be a state. So when I press next, it is going to the next day. So 3 days back, we had seen the same state. Do you remember we had this discussion and we made a guess whether 16 will be alive and who will be dead and blah, blah. So we reached the same state. So the rules of the game are such that it is only dependent on what has happened yesterday. It just looks back one day. It doesn't care about what happened day before yesterday. It doesn't care about what happened tomorrow. It only looks at one day before, and the tomorrow is created based on today. That's all it looks at. So the moment you reach a same state which you had earlier reached, the next state from that point of time will also be the same as the next state when the same was achieved earlier. It cannot be different. You cannot reach a same state 2 times and go to different states from that. No, you will reach the same pattern of states once you hit a pattern which was previously achieved. So now we know for a fact that we have reached a situation where this cycle will repeat and this game will progress in the same way that it did 3 days back. So let's go next. We again have the situation where only the 4 corners are there. Once again, I will explain to you why 1, 4 and 13 will live, 16 will die, goes here, comes back here, and finally reaches here again. So we reach this 4 cycle. So let me count the cycles. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. The same 4 states will keep repeating forever. And that is where this game becomes interesting. Nobody has a clue when it will happen. Nobody knows how it will happen, but it will happen. And the simple explanation as to why it will happen is because we have only finitely many numbers in our grid. Each of them has only finitely many states, which are either 1 or 0, which is either, they can be excited or dormant. So even in the worst case scenario, you have 2 into 2 into 2 into 2 into 2 to the 16 number of ways in which these people can form patterns. And 2 to the 16, although it's a very big number, it's a finite number. So you will know that eventually you will have to reach a situation which you have seen earlier if you wait long enough. And we didn't even have to wait long enough. It just took us, let us count how long it took. 1, 2, 3, 4, 5, 6, 7, 8 steps. It took us 8 steps, and the 9th one which we reached was the beginning of a cycle. I want to point out something really interesting, okay? I want everybody to observe really closely the state which we have before we reached that state of the entire city being colored, right? There was only one corner missing, everything else was colored. Before we reach that, let us observe what we have, okay? Before we reach that. So I will tell you when it is. I hope I remember it correctly. No. I think this is the one. I think this is the state which is one state before the entire grid being colored and only one corner being non-colored. So let us verify and let us observe this very carefully, okay? So we have 1, we have 4, we have 8, and we have 14 and we have 13, okay? That's it. Remember 1, 4, 8, 14 and 13. I don't know how to remember this, but let's try to remember it. Everyone else is dormant except for 16. Now we reach this, okay? Now, let us see if that same state of 1, 4, 8, 14 and 13 and 16, do we get that same thing again before this guy comes up? Okay, let's observe. So we now went into this pattern. We went into this pattern where we know that it is repetitive. Right? This is what we get in the pattern. But what is the state before that? It is this one. And although this guy is the state we are getting before we get that entire grid colored except for 16, it is not the same as the one that we had earlier. The one that we had earlier was 1, 4, 8, 14, 13, and then we went into a situation where the entire grid was colored except for 16. But now we have 1, 4, 9, 14, 13, and the next state is everything is colored except for 16.
So that means that we can have different situations which lead to such a thing.
Nope, that's not what it means. That's why I wanted to show you this thing. Let's observe again. Let's make sure everyone is understanding and let us check if our guess is correct. So we have this situation 1, 4, 8, 13, 14, 16. Okay, everybody can watch 1, 4, 8, 13, 14, 16. Forget about the game, forget about the rules. Just look at which are the numbers which are colored. Okay, we have 1, 4, 8, 13, 14, 16. 1, 4, 8, 13, 14, 16. The next state is where we have everybody colored except for 16. Okay, everybody is colored except for 16. That is what we have. Now let us go forward and check. We have 1, 4, 9, 13 and 14, and everybody is colored. So it's not actually the same, because the 16 guy was not colored in this case, but he was colored in that state. So it was not exactly the same. So I am not that happy now. I thought we reached a situation where the previous states were not the same. Oh, sorry. Hold on. Yes. Okay. Wait, sorry. So now what do we have? We have 1, 4, 9, 13 and 14. Okay. These are the people who are excited. But still the next state is this. In the first case, what had happened? We had 1, 4, 8, 13, 14, 16. And the next state was this. Okay. But now we have 1, 4, 9, 13 and 14. And the next state is this. So we had two different states which led us to the same state. What does that tell us? What does that tell us? So somebody said that, oh, so this means that they are not unique and we can go. No, that's not what it means. My claim was, once you reach a state, the next state will always be the same. Meaning, let us use some variables here. Okay, let's say there is state A, and the next state is state B, and then you have state C. Okay. So what I'm saying is, every time you reach state A, the next state will always be state B. But it could also be that every time you reach state Y, the next state will also be state B. We never said that two different states cannot lead to the same state. That is still possible. We just said that if you reach one state, the next state will always be the same as what happened the previous time you were at that state. So here what is happening is that 1, 4, 8, 13 and 14 and 16, that state is leading us into this guy. But also 1, 4, 9, 13 and 14 is also leading us into the same state, which is really interesting. So this tells us that this game can work in weird ways where you have completely different looking states leading to the same looking state. So yes, so as Sundar is saying, this is not an injective function. Those of you who have studied functions, it is not a one-to-one mapping. But it is surjective because we know that every state will have a predecessor. So it has to be a surjective function, but it is not injective. You can have two different states leading into the next state, which is going to be the same. But if you think about it a little more carefully, it has to happen that way. Okay, it has to happen that way because that is the only way by which this game can reach a cycle. You have to have two different states leading to the same state. Otherwise, it's not possible. Unless the entire game itself is a cycle, which means the first state itself is a part of a cycle. So you have 1, 2, 3, 4, 5 itself as a part of a cycle. Again, you have 1, 2, 3, 4, 5. But that is not going to happen. We know that that's not going to happen. And maybe in some cases it will, but in most cases it is not. So the cycle is starting after you start the game, after a point of time. So what that means is that one number which was there before the cycle started and the last but one number of the cycle will both lead us to the first element of the cycle. Are you understanding this? So let us think about it like people are standing in a line. Okay, everybody standing in a line. You have number 1, 2, 3, 4, 5, 6, whatever. And we say that from some point of time, people will start going in circles. From some point of time. But that circle doesn't start in the beginning. The circle only starts after a point of time. So actually, let me draw it on the board to make it interesting. Okay. Let us try to understand what exactly was happening and let us get a better picture of the whole thing. So let me stop sharing my screen and you can look at my board. Okay, so let me. Okay, so I have a marker and it's pretty good. Let's see if you can all see it clearly. We have this line of people who are standing like this. Okay. And at some point of time, I claim that there will be a cycle, which means people will start going around in circles. So it will be like this, okay? And from that point of time, everyone is only going around in this circle. And this is happening in every grid that we start with. Okay, that was what we studied. So this is the game start, and this is the cycle. So if this situation has to happen, just think about it in an abstract sense. Don't think about the game of primes, just think about this diagram. What it means is this guy here, A, and this guy here, B, okay? So this guy here is B, and this guy here is A. Let me write it clearly, okay? Okay? This small line here is B, and this line here is A. Both of them have to lead to this guy C. So A is leading us to C because we went like this, and A was followed by C. This is C. And then we went like this, and then we reached this. But after this also we had the same thing. So A and B both have to lead to this same line over here. And after that point of time, A will never come again because A only appeared once and it was the first time and the last time that A appeared. After that point of time, we only have this cycle as part of our whole game. This initial chain, now let us call this entire chain as the beginning, okay? And this is our cycle. So this entire game in every grid is divided into two parts. It either has the beginning and then it has the cycle. And both of them are finite because remember this entire chain has to be finite. No matter how big your grid is, as long as your grid has a finitely many elements in it, which means finitely many rows and columns, this chain also should be finite. Okay? If this chain is finite, what it means is this is also finite and it also means this is finite. So both these are finite. That's what it means. The question is how long is this chain? And the other question is how long is this chain? Those are the two things which are most important when we study the game of primes. The first question is how long is this chain, which means how long do we have to wait to see the beginning of a cycle? That's the first question. And in the grid that I showed you, which was the 4x4, we had to wait about 8 steps. We had 1, 2, 3, 4, 5, 6, 7, 8. Then we had this particular grid, which had everything colored except for this one corner over here. Everything else was colored. We reached this situation, which was the first element of our cycle. So this guy was this person over here, C. This guy was C. The person before that was the thing that I told you, remember, right? 1, 4, 8, 13, 14, 16. That was A. B was 1, 4, 9, 13 and 14. So that's what I told you, that A and B are two different, but they led us to the same situation C. And from that point of time, we had a cycle, and the cycle was, I think, 4 steps long. we had this one, and then we saw everybody dying and only the four corners being alive. Then we saw that the three corners were alive, and again people got life, and this guy died again. So there were four states, and then it repeated. So those are the two questions. How long does it take to reach a cycle? And once we reach a cycle, how many steps is the length of the cycle? How long is this? Because I have an example of a 10 by 10 grid where it only takes us, I mean, the cycle is only 6 steps long. Basically, the entire cycle is only 6 steps long. This whole thing is 6 steps long. But to reach a cycle, it takes you 600 steps. So for the first 600 iterations, 620 something, you have no two things that look the same. And then you have a cycle. So it's a very interesting problem. And I have listed out many examples and I've studied their patterns, and there is nothing that we can say for sure. Like there is no formula that we can come up with. It is just totally random. Sometimes this is really long and this is short. Sometimes this is short, this is long. Sometimes both of them are long. Sometimes both of them are short, and it's totally random. But we know for a fact that both of them are finite. And before I finish, before we get into the discussion section, I would want to say one more thing. The first conjecture that I made for this game was that the length of this guy is always even. The length of this cycle is always even. That is the number of steps it takes, 1, 2, 3, 4, 5, 6, whatever, to come back and inside this structure is always going to be even. And that was the first conjecture that I came up with for this game. And I think at this point of time, I would like to stop the recording, and then I will allow you all to think about this and digest it, and then we can informally discuss it. Okay. Thank you so much, everybody.